All right, so how are things going? Finished PA2, good. Finished PA1, even better.
I finished PA2 like yesterday.
Cool. Is the transition from PA1 to PA2 making sense?
Oh yeah.
Right.
Fun.
Cool. Excellent.
Yeah.
I've given that pair of assignments before, and sometimes I do PA2 first, and then PA1. And sometimes that makes more sense for people to start off with the pointers and the mallocs and all that, and then do arrays. So it's hard to know, but hopefully the combination is working. So any sort of last questions on PA2 or issues that people are running into? So let me talk a little about Valgrind. Some people are discovering when they run Valgrind on their program, even if it says no memory leaks, you're getting lots of warnings and error messages while your program is running. Those are worth paying attention to. If Valgrind is complaining about something, there is a potential problem in your code. Okay, and it may not cause your program to misbehave, but there's something that you should try to figure out and work to clean up. And typically it's an uninitialized variable. And this can happen, for example, when you create a struct node, chances are the next field is already equal to null. But if you don't explicitly say, you know, on a new node you're creating at the end of a list, if you don't set node arrow next equal null, you can't guarantee that it's equal to null. And that's something Valgrind will pick up on, because you're using this field that was malloc but not initialized. If you free something that's not actually a node, you malloc. If you free something in the middle, like if you try to free node arrow data, for example, you'll get warnings from Valgrind. And it may actually free what you're trying to free, but it's not quite right. So really, Valgrind should give you a pretty clean experience. And if it's giving you warnings or errors while you're running, there's something to check into. Now, don't break your code trying to get rid of those, right? If you're going to start making drastic changes, always do it on a copy. But pay attention to them. It's kind of like compiler warnings, right? A warning from a compiler isn't going to stop your program from compiling, but there's probably something that's not quite right. And maybe it's harmless. Maybe you're printing a pointer as an integer, but it's just something you want to look at. That's not a big deal. Or maybe it's you should have an integer here and you only have a character. And maybe if your integers are small, your code works fine, but if your integer gets to be big, suddenly your code's going to break in some dramatic fashion. So if you find those things, you can ask about them. All right, on to PA3.
I do have a question about PA3.
Yeah.
Do we have to use the hash function you give us?
Mm-hmm.
'Cause it's really bad, like as far as collisions and stuff.
Yeah. Is it?
Just to add the characters up? That's
Yeah.
what it was, right?
Well, it's adding the characters multiplied by the position plus 5.
Oh, I didn't hear that part. I thought you just said it's just adding them.
Your hash function is,
Did we do the sum, I think?
yeah, it's this.
Oh, okay. That's not so bad.
Okay.
Yeah. Because I was just messing around and I got like 1,000 collisions.
Yeah, yeah.
With 1,000 pieces of data. Wow.
Yeah, that would be pretty bad. All right, so yeah, as I hinted the other day, so you're implementing a hash function. Let me show you what this does first, and then we can go through the details. So there's a sample executable, and you want to use this sample executable to figure out what your program should be outputting, how things should be formatted, and to make sure your code's running the correct way. Okay. So there's two things in temp. There's a file called database.txt. It's a bogus database of license plates. So these are randomized license plates, and I found a web page with 1,000 first names and 5,000 last names, and I randomly pick one of each and put them together. So these are fictitious names. As far as I know, there's a Dirk Macias in here somewhere. But the whole file is just license plate, first name, last name, separated by spaces. The license plate isn't always 3 letters, a dash, and 3 digits. It could be anything. But it's basically anything up to a space, and then a bunch of stuff up to a space, and then a bunch of stuff followed by a new line. And you interpret it as license plate, first name, last name. So your program, which is going to be called plate, executable has to be called plate, and there's a sample under /temp. You run this, and you have to specify the name of a database. Now it can be your own database, or you can use /temp/database.txt. And if you want, you can specify how big you want your hash table to be. That's an optional parameter. Things in brackets are optional. It defaults to 100. So I'm just going to run plate on this database file, and it says enter command or plate. So I can put in a license plate like YGG-155. That's Claudie Powell up there at the top. And it tells me first name Claudie, last name Powell. I can put in a different plate, and it'll say plate not found. So it's just a lookup function. But the whole point of this is that when you first start this program, it reads this file, and it builds this data structure called a hash table. And it's a more efficient way of looking things up than just going through and searching every entry. Now you could make the behavior that you see here with a big array. You just read everything into a set of arrays and then just search the plate array and find a matching name. But that's not the goal. So you can search plates and so on. Okay, additionally, it understands a couple of commands. So if you say *load, that's a command which says, show me how heavily the hash table is being loaded. Now it's a hash table where each entry in the hash array is a sentinel node, so we're using this technique called chaining. Each hash entry points to a linked list. The load factor can be thought of as how big are these linked lists. And I've got 1,000 license plates I've read in, and I only have 100 cells in my hash table. So I would expect each entry to take about 10 nodes on the linked list. That's a really heavily loaded hash table. If I say *load, it should give me the following output. For each entry, tell me the length of the linked list in that cell. So entry 94 only has 3 things. Entry 90 has 18 things. Okay, the second command you can use is dump, and I can say, for example, let's dump entry 94. This just means show me the contents of that node. And so that's what that linked list looks like. It has 3 license plates. There's the plate, there's the name, and the name is last name, comma, first. Yeah?
Sorry, what does length,
That's the length of the linked list.
the linked list?
Yeah. And it's also the number of license plates stored in that cell, effectively.
Okay.
So entry 90 up there near the top, it says length equals 18. If I say show me the linked list in cell 90, right, I get 18 nodes in that list.
Why is there so much variance between?
Because the hash function is kind of whatever I dreamed up when I was writing this. Now, if you hashed every possible key, it would probably end up even, but these are random license plates, so there's no reason we would expect them to be evenly distributed. But, you know, something approximately even would be pretty nice. Well, I mean, there's a lot of them around, like 10-ish. There's some 8s and some 12s. But then there's some outliers, like 17, or 3. All right, so 2 commands. Asterisk uppercase load shows you the length of each linked list. Asterisk uppercase dump followed by an integer, in this case between 0 and 99, shows me the elements of the linked list in that cell. And if I try to say, you know, something that's not valid, it just assumes I'm looking for a license plate. If I say dump and I put in a negative number, or I say dump and I put in a number that's too big, or I put in something that's not an integer, oh, my bad, Don't look at that.
Just force it.
Yeah. Right, so I should fix that. And if you just say dump without a cell number, it'll dump every cell. Okay, it'll show you the contents of everything that's in your linked list. And I'm going to be really picky about the formatting of this. This is part of why you have a sample executable. So I want to see contents of cell and the cell number, and then plate colon, and then name colon, last name, comma, first name. Okay, but when you actually do a lookup, like QCO 897, I want to see 2 lines of output, first name colon, last name colon. There's a reason I'm being specific here. Okay, so those are your only commands. Star dump, possibly followed by a number, star load, followed by nothing, or a license plate. And you know, anything it doesn't understand, it's assuming it's a license plate.
Is there an exit command?
Control D, so
Okay.
you exit with end of file. Okay, so if you're reading these plates from a file, when you get to the end of the file, it'll register as EOF. If you're asked to enter the plate, hold down Control, press D, that triggers end of file. And then you want to free your memory. So if you run all this in Valgrind,
What was the double exclamation mark there?
recall the previous command. That's the one that got stuck in my brain last night. So when you're done, hit Control D, should come out with a nice clean exit status. Now, I called malloc 4,100 times and allocated 64K dynamically. So there's a lot of mallocing going on. So freeing is a little more challenging than in PA2, which is challenging in itself. But that's the intended behavior, okay? So make good use of this executable and sample database, but make smaller databases if you want. Oh, and if you specify how many cells you want in your hash table, so if we make a hash with 10 cells, right, then each linked list is around 100 entries long. And if I, look at one of those, it's got a whole bunch of data in it. And if you make your hash table really large, then most of your cells are going to be empty, right? And you'll find some that might have 1 or 2 nodes in them. But interestingly, most of the higher ones are unused. There's one at entry 5379 that got a plate in it. But since I'm adding up ASCII codes, and most of my plates are only 7 characters, it's going to be really hard for my sum of 7 ASCII codes weighted to get up into the 5 or 6 or 7 thousands. So we kind of expect that mostly it's going to be the earlier cells in the hash table that start getting a lot of stuff in them. So yeah, so this is an example of clustering, right? Because ASCII codes vary between 65 and 91 or so, right? And since I'm using the same hash function on the same set of ASCII codes, I'm finding a lot of packing in, right? A lot of things are hashing to things around 3,200, 3,300, 3,400, and then around here it starts to fall off. So I've got 10,000 entries in my hash table, but I'm only really using a few hundred of them. It's a bad hash function for this type of data. And if we look at 5379, all right, so that had a license plate that happened to be longer than the others, which is why it hashed down to something further.
You do that one on purpose.
No, I hadn't thought about this till 2 minutes ago. But yeah, I put the data in on purpose. That's not random. Okay, it's got the idea how this thing looks when you're running it. Okay, so it's a 6-page write-up because there is a lot of detail here. Part of your goal is going to be just to digest these 6 pages into a form that you can work with. Okay, I've got everything in here as far as I know that you need to know, but you're probably going to want to paraphrase this in your own way. So introduction, this is what we've already done, right? You can enter commands or license plates and it'll pull it out of a hash table. Behavior, we've kind of already said, so when you run your program, the output should be really close to what you're seeing in the sample. So for example, if you say plate not found uppercase instead of plate not found lowercase, you're okay, all right? If you don't print anything when the plate's not found, that's going to lose points. If you segfault when the plate's not found, right, that's a real problem. If you print out first name, last name instead of last name, comma first, that's a big problem, okay? The reason being there's a lot of ways to do this differently from what I'm asking that make those types of output harder to do. So try to stick to the output format as closely as possible. Startup, it's either plate followed by the database name or plate database name and how many entries you want in your hash table. If you don't specify hash table size, it defaults to 100. If you try to run the program in any other way, you don't specify any arguments, you specify more than 2 arguments, you don't specify a valid integer that's bigger than or equal to 1 for the hash table size, print out an error and exit. Okay, so really strict usage requirement. Assuming that they used one of these 2 ways of running your program, open the database, read it in. If you can't open the database, print an error and exit. Okay, if it's a non-existent file, if you don't have access to it, just kick them out. Input file looks like this. We already saw that. License plate, first name, last name, separated by spaces, new line at the end. Don't forget that there's a new line. You want to strip that off. If you don't strip it off, your hash function will come out totally different from mine. So the last name is Hubbard, H-U-B-B-A-R-D, no new line. So you got to remove that. Anytime, say,
The spaces are okay with?
the space is not part of the name. So the first name is V-I-T-O, the last name is H-U-B-B-A-R-D, the plate is RRW-885.
Right.
And the spaces are just to delineate the fields. The new line is just to delineate where the last name ends. And if your program exits for any reason abnormally, return a 1. If it exits normally, return a 0. So make sure your main program is an int, and when you say return, return 1, return 0. All right, so you can put in a plate, it'll print out the information for that plate or plate not found. You can put in any of these 3 commands. And here's some more examples of the output formats. So for a license plate, that's the format. For the load command, this is the format. And for the dump command, show you the contents of a cell, or if you just say dump, do this for every cell. You exit with Control D in the beginning of a line if you're doing this interactively. You can't type something and then hit Control D. That's not end of file. End of file is signaled by at the beginning of a line just holding down Control, hitting D. Okay, that'll act like a new line, but it'll cause fgets to return EOF or to return null, which means EOF. Don't exit under any other conditions. Right, if they put in a plate and you don't recognize it, if they ask you to dump cell 2000 and there is no cell 2000, right? These are errors, but you don't exit the program. The only time you exit the program is when the person says Control D at the beginning of the line.
Do you want specialized, like error commands?
What do you mean?
Like, if they try to access a cell that doesn't exist, do you want us to say error cell does not exist for like all of the edge cases?
Yeah, so if I say right, so if I try to dump an illegal cell, I didn't go crazy with scanf, so since it's not an integer, it thinks it's a license plate search. It's a little sloppy, but that's okay. All right, so you hit Control D in the beginning of the line. The program should exit. Before you exit, you want to free your memory. Okay, so implementation. This is the gory part. Okay, you're going to implement a pair of data structures, linked list and a hash, because your hash is going to be comprised of linked lists. Okay, and the linked list you've already basically done in PA2. So the real new part is the hash table. Okay, linked list first. The nodes of the linked list look like that. They have 3 data fields: a plate, a first name, and a last name. And then they have a pointer to the next node. And I want you to implement it like that, as opposed to stringing all the strings together into one string or something like that. So character plate, character first, character last, and then pointer to the next node. There's a sentinel node on the list, same as always. And other than that, the list is basically what we've been doing from the beginning. Okay, there's a hash table, which is an array of pointers to sentinel nodes. So an array of pointers to sentinel nodes. So if this is hash table, it's an array. Each of these is a pointer to a sentinel, which means it's a struct node star. Yeah.
This is kind of similar to nested arrays.
Kind of, yeah. All right, pointer to a sentinel node. If we think of a type def, if we were to type def a struct node star to something we call hash entry, then each one of these blocks, this is a hash entry. Okay, it's really a struct node star. But by calling it a hash entry, well, if it was an integer that I wanted an array of, what would I say? I would say int star. If I wanted an array of characters, I would say character star. If I want an array of hash entries, what do I say? I'm going to say hash entry star. That's what my hash table is going to be. Now, if you undo the type def, what is a hash entry? It's a struct node star. So a hash table is a struct node star star. But that tends to get confusing, right? But that's like argv being a star star. It's a pointer to a pointer, which means it's an array of pointers. So if you think of the type def, just think of each of these things as a hash entry. Whatever that is, if we want an array of them, just say hash entry star, just like int star star star. That's potentially the most confusing part of the whole setup, right, is what should the hash table look like. So hash table is comprised of an array of struct node stars, which is an array of hash entries. So your hash table is a hash entry star. Okay? You can't predefine what the hash table size is, so don't say hash entry hash table bracket 100, because the person might decide they want 5,000 entries in their hash table. So you're going to set up the actual array dynamically when your program is running. But to declare it, you just say hash table is a pointer to a hash entry, which says it's an array. Also, do not make any assumptions about how big or small these strings are. This is a string, that's a string, that's a string. They might be very short, they might be very long. We're going to dynamically allocate space for those when we need them. All right, so your hash function, add up the ASCII codes of each character multiplied by 5 plus the position of that character. It's a randomish function that I just pulled out of my head, just to give you something interesting to code. So if our string is hello, Hello, the length of that, so I'm calling this plate, is a string. The length of hello is 5, so we're going to do a sum from I equals 0 to 4. Which is going to look like this. So hash table size is coming from your command line argument, or it defaults to 100. Don't make it global. It doesn't have to be global, but you're going to want to pass it to your hash initialization function. But in main, main is the only thing that has to know what that is. Okay, so if we wanted to hash ABC, that's going to be the sum from I equals 0 to 2, okay, of I plus 5 times the corresponding character of our string %. Let's say our hash size is 100. Okay, so what is this going to be? For index 0, this is going to be 5 times ASCII code for A. And then I is 1, it's going to be 6 times the ASCII code for B. And then it's going to be I equals 2, 7 times the ASCII code for C. So these are ASCII codes. And this is coming from the I plus 5s. So do that addition, divide by 100, take the remainder. And you get a number between 0 and 99. What that hash function is telling me is that if I want to store ABC in my hash table, it's going to be in the linked list at this index. If this is 92, then it's going to be in linked list number 92. I go to hash table bracket 92, that's the sentinel node of the linked list I want to store this node in. All right, got an idea on the basic setup? Okay, so here's the functions you want to implement. A series of hash functions, and these are the only functions your main program is going to use. Your main program is never going to deal with linked lists. Your main program is only going to deal with the hash table. The hash table is only going to deal with linked lists. Okay, so there's a hierarchy here. There's a main program which talks to the hash functions. The hash functions talk to the linked list functions. The linked list functions go down and deal with null and arrow next and all that kind of stuff. All right, so hash init, pass it an integer, which is how big the hash table should be. It returns this array of hash entries. Hash add, you pass it the hash table, that's the array. Pass it the plate, the first name, and the last name. And it will add that to the linked list associated with that plate. And when you're inserting into the list, always insert at the beginning of the list. We don't need to keep it sorted because that doesn't help us. So anytime you're inserting into a linked list, just put your new node right after the sentinel. So it's a really quick operation. And then hash find, you give it a hash table, you give it the plate, and it will run that through the hash function, find out where in the hash table that should be stored, go down to that linked list, search for this plate in that linked list, and if it finds it, it will load the first and last name into these two strings, and the function will return a 1. If it doesn't find the plate, the function just returns a 0, and these strings are unchanged. So it's kind of like scanf. right? It will update the value of these fields if it finds what it's looking for, and it will let you know that that happened by returning a 1. And if it doesn't find the license plate, it just returns a 0. Hash load basically tells you the length of each linked list in the hash table. So this function will actually do some printing. You give it a hash table, it'll just loop through from 0 up through hash size -1 for each one, find how long the linked list is, and print that out. Hash dump, you give it the hash table in a cell, and it will print the contents of the linked list in that cell. And then hash free frees all the memory associated with a hash table. Now here's the glorious thing about this, and this is probably the most important lesson from this assignment. Hash load, well, let's look at hash print. Hash dump, right? I've got a hash table, I've got a cell number. Well, we know that your hash table is a collection of pointers to sentinel nodes. So if you say hash dump 3, what do you want to do? You want to go down to element 3 of your hash table. What I find there will be a hash entry, which is just a pointer to a struct node. In particular, it's a sentinel node. If I have a package of functions for dealing with linked lists, I should have one which prints out the contents of a linked list, the print function from PA1 and 2. I do not need to write that function in my hash dump code. My hash dump can simply say, hey, list print, parentheses, give it the name of the sentinel node. And if I have this list print function that I wrote for PA1, PA2, that traverses the list and moves the pointer over and looks for the thing pointing to null and all of that stuff, right? I can just call that. I can say, hey, this entry is a sentinel node, pass that to the function that prints a list given a sentinel node, right? So my hash dump function does not have to do anything listy. Okay, this is the key to code reuse. This is the key to modular design. This is the key to success when we start working with objects in 223. And the same thing goes with all of this, hash load. Well, if my linked list comes with a function which says length of list, right, I can just say for I equals 0 to hash size -1, print length of list, parentheses, hash table bracket I. And same thing for add. All right, so for adding, I have to run my plate through a hash function that gives me an index, and then I say, okay, at that index I find a sentinel node. Now I call the add function, give it the sentinel node, give it the data I want to add, and it'll make a node and pop it on there. So these functions are new to this assignment, but they're mostly just wrappers around things that we've already done. So the list package, right, there's list init, we've done that. There's list add, takes a sentinel node, takes the data we want to add, and instead of an integer num, we've got 3 pieces of data we want to add. So make a new node with malloc, set the plate first and last fields from here, right, string copy, and then have that thing point where the sentinel's pointing, have the sentinel point to this new node, and return. And I didn't bother with return values from these functions because we shouldn't run out of memory. So these functions are void. List find is just the search function, right? So go through and search for a node that has that license plate on it. And instead of just returning a 1 or a 0, if you find that node, it's also got a first name and a last name in it. So go ahead and load those into the arguments that were passed to you. List len is like print, but instead of printing, just keep count of how many nodes you have. List print is just like print from PA1, 2, but you have to print additional pieces of information, the plate, the first name, and the last name. And list free, you've already done, or are doing for PA2. And so how do we free the hash? For I equals 0 to hash size minus 1, list free hash table bracket I. That'll free all the memory associated with the linked lists you created, and then just free hash table. Okay, suggestions, start early, as in today or yesterday. But don't start coding right off the bat. Spend some time going through this write-up, parsing what I've said here, putting it into your own format, however you want to organize it for yourself. Checklists or whatever, right? There's a lot of pieces here. But it's still something that you can start small and build up. Okay, just make sure when you're doing that that you have something you can go to know when you're actually done. So look over the function prototypes, think about how they're going to go together. So yeah, this is the punchline again. Adding to the hash is really just using the list's add function. All you have to do is figure out which list you want to add to. And that's using your hash function, right, which is the weighted sum of the ASCII codes of the license plate. So I've got some suggestions here for how you might break it down. You can read through that. But the last paragraph is worth noting, right? If you're getting stuck or you aren't sure how to proceed, ask me, okay? But try to start with something that you're pretty sure you know how to do. Get something going, right? And if you've done PA2, you've got a big chunk of code to build on, right? You have to change the names of the functions. You have to change what the node looks like. But you've got the core functionality and all the tricky parts of moving the pointers and that kind of stuff, right? So start building up from there. But definitely come and ask me questions, right? Shoot me a note, something. And don't let this go for, a week before you start looking at it, because it's going to be really overwhelming if you only have a week to do this. All right, submission on GitLab repository must be named plate PA3. Uppercase P, P, uppercase A. Add me as a reporter. Okay, you need to include your .h files, your source code files, those are the .c's, and a make file. Don't include the .o's, don't include the executables. Okay, but include everything that you need to make the executable. And I strongly recommend, before you say that I'm done with this, you've pushed everything over, go into a completely empty directory on your machine, do a git clone to pull down your repository, say make, and then say plate/temp database txt, and make sure it works. If it doesn't work, you're looking at a 0, okay? Because if it doesn't work for you, it's not going to work for me. So it's like an acid test, right? You've got the code, it's working for you just fine, you push it over. Maybe you forgot to push the make file, maybe you forgot to push the hash.h, right? Little omissions like that, I pull down your repository, I say make, and it doesn't build, right? And so now it's late and it's 25 points off. And if you don't get my email by Sunday, it turns into a 0. So it's really easy to have these little omissions have something that's not quite right. And you can take care of a lot of those by just do what I'm going to do. Go to an empty directory, git clone, make, plate. And make sure all of that works. And that catches those last minute changes that cause compile errors and omissions and things like that. So we want to think about this modularly, but if we think about what's actually going on, hash table looks like this. And let's say we initialized our hash to be 5 cells. Well, each of these is a pointer to a sentinel node. And the sentinel node contains the following. It contains a license plate, a first name, a last name, and a pointer to a new node or null. So these are sentinels. And this is a struct node. And so if we get the plate ABC 1, 2, 3, and this is Bob Jones, right, we create a new node. Put the plate up here. Put the names in. Have it point where the sentinel's pointing, have the sentinel point here. How did we know it goes in this list instead of this list? Well, when we first got ABC 1, 2, 3, we called our hash function with the license plate. And suppose that returns a 1. Well, then we start with the sentinel that's stored at location 1, we add to that list.
You said we're always adding it to the front of the...
Always add it to the beginning of the list, yeah. Because it doesn't really matter where it is, and that's the easiest place to add. PA1, we wanted it sorted, but that was just to give you something to do. It doesn't actually make searching any faster. So we can start writing out some pseudocode today or Monday, but this is the basic setup. And none of the pieces of this are particularly complicated. The init function, the add function for the hash, the add function for the list. Most of these are going to be a few lines of code, right? So it's not going to be, 50 lines of C code. But the trick is, what the heck is this supposed to do? What are the right 4 lines of code to put here? And the answer to that comes from understanding, right, what we're trying to do, how we're building up this structure. So this is a structure of structures, right? The hash table is a data structure built on an array, which is comprised of linked lists, which are built of struct nodes. And inside those struct nodes, we have strings that are dynamically allocated. So when you want to create a new node, we might do something like this. If you want to create a new node, we're going to pass it a plate, a first name, and a last name. And so we can make a temporary struct node. And what are we going to malloc? Size of struct node. All right, if we're just storing an integer, now we just say temp arrow data equals num. Can't quite do that here, okay? Now I could do this, but don't. Don't say temp arrow plate equals plate. What's wrong with doing that?
You never initialize the plate.
A plate's an argument.
It's a variable, it's a local variable.
It's a local variable, right? It is pointing to the characters making up a license plate we want to store, but the next time I call new node, the place that this is pointing might be something different, right? It's a local variable, so this is going to temporarily put a good license plate into there. Once my function exits, it goes kablooey. So we need to use string copy. That's better.
Wouldn't you still run into that issue though? Because you didn't say in your struct node definition that the plate holds X amount of.
We haven't said what the plate holds.
You need a malloc.
So we need to malloc, right? Now, if I had declared in my struct node that plate was an array of 100 characters, this would work fine unless I tried to store 110 characters. So we're going to set this up dynamically. So we need to make space for the license plate. So plate equals malloc. Well, how much space should we malloc? And this is where using size of plate or size of star plate will get you into trouble. Because size of star plate is 1, size of plate is 8.
It's like size of car times string length of.
Yeah, so we're going to use string length. So take the length of the plate. Anything else?
You could multiply by the size of the.
And we could multiply by the size of a car, right? I'm going to assume cars are 1, but yeah, multiply by size of car. We got to do one other thing. This is
3 plus 1.
why?
Because they don't.
Because of the null terminator. If your string is HELLO, string length is 5, you actually need 6 bytes to store that string if you want to include the null terminator. And if you don't do that plus 1, oh boy, all kinds of things happen. Because it'll put the null terminator somewhere, and for small test cases it'll work fine because there's always padding. And then you run it on the 1000 and you'll get all kinds of fireworks coming out of your cooling vents and stuff like that. So, and this is a common thing that pops up a lot when we start doing dynamic memory. So we need a plus 1 there. All right, play around with that. Talk about algorithms. Write some ideas down, and have a good weekend.